Okay, picking up where we left off, we're on page 276 or so, talking about the default router, the default route. I mentioned that PCs have a responsibility. They know what's local and they know what's quasi-local. And then they know everything else is just send it to this other router. I know companies that even if they have interior routers, they don't bother with those guys. So what happens is you send all the foreign requests, go to the edge router. The edge router says, well, this is not really foreign, so I'll just send it to one of my interior guys. It makes things simple. You know, it's incredibly simple to configure, but you are kind of wasting a hop, because if the machines knew how to talk to those interior guys, it would be one hop over versus 2 hops over. Okay. So smart people, if you care about speed, well then you probably configure it one way. If you don't care about speed, well then you don't configure it that way. Okay, I'm going to show you some more stuff about how you can figure out the routes between point A and point B. So the first one is going to be trace route. Now this is probably, and this is back in the DOS days when they had 8 letters, right? So it's TRACERT. Okay, that tells you something. I'm going to use the same one they have in the book, which is Wall Street Journal. Now this may take a while, and so I may do some magic here in video editing to speed this up. Okay, that wasn't that bad. I don't think I'm going to have to speed it up. So get to my machine to the Wall Street Journal took 11 routers, 11 hops to get from point A to point B, and here they are. So the 10 dot, that's me, goes to a default router, which goes to another default configuration inside the router, and then hops on some Roadrunner Time Warner backbone. I don't know where this is, and yet another one, someplace in Texas, and then some other Texas backbone, and something. And so anyway, 11 hops later, I ended up getting there. So it took quite some time to produce this, right? So a packet leaving here is kind of delayed for a couple milliseconds, and then delayed again, and delayed again, and delayed again. So each one of these hops has a cost associated. No, I bet, poor choice of words. Is consuming resources. It's slowing down. So the fewer the hops, the faster these things would go. Okay? So again, you would hope that Time Warner has my best interest at heart, and so they've configured this to give me the lowest amount of transmission. But you don't know that. Okay. Okay. That's kind of the thing. There's another way you can do this, that if you just say route print, it's going to dump a bunch of stuff. This is going to show you the entire contents of the route table. Now, just like the example we had in the book, so let's just go through it. So here we go. So right off the bat, here's my interfaces. I'm only using interface 10 right this very second. So here are my active routes. This is the default. The default basically means, look, if I don't know anything, broadcast, here's how I do this. So if my destination is 10.2, then here's my subnet mask, and that's how I do that. And if my thing just goes through dot. So these are those broadcast guys. Remember all those guys? And then this one basically says, if you can't figure out what it is, then send it to my router, and I'll figure it out. So here they are. Here's the IPv6 version of that same thing. What the metric is, the destination, and whether or not it's currently turned on and running. I don't have any persistent routes. All of mine are dynamic. So this is a way to view the contents of the routing table on your PC, not the routing table in the router. And by the way, these routing tables could get big. If you're one of those autonomous systems, a big autonomous system that has thousands of routers, okay, this table could be monstrously huge. It could be, one of the stories they talked about was when they were setting up the IPv6 thing, that They had to send all the new routing tables around because they were swapping out parts. And one of the routing tables was 900 megabytes of routing table. Wow, that's big stuff. Okay, so this is about how how to understand how routing takes place, and succinctly, two models. One model is I know exactly how to get from point A to point B. Typically, those are the interior guys. And there's actually a class of routing called interior routing. So the interior routing protocols, I'm not going to go into details, they basically know everything. They know the location of every single PC. They know the exact path to go between my PC and the printer, and my PC and the file server inside my network, okay? Now, just think about that just a minute. So I only have like 400 or 500 machines in my hypothetical business environment. I got a handful of routers. And so there's probably not that much in the routing table, is it? I mean, I only got like 400 or 500 machines. It's like, no big deal. But how scalable do you think that is if I was to bring that up to the internet? Ouch. The internet routers cannot know the path to every single machine on the internet. No way. So they do the other technique. Inside my router, if I want to go to Lampasas, I'm going to give you the full path. First you go to Copper's Cove, then you go to Kempner, and then you go to Lampasas. Inside my network, full path. Because I can afford to store the full path. Outside my network, it's go to Copper's Cove and ask them. One hop only. Because I just can't keep all that information. The only thing I can really keep is how to get to the next edge. Okay. So, thankfully, in this class, we're not going to go through router protocols, but they are in two major categories. The interior protocol, the interior guys who know the full path and typically make very good decisions based upon what lowest cost. And then you have the exterior guys, and the exterior guys, well, it's kind of policy based, and you hope they have your best interest at heart, and they do not store the full path to anything. They store only how to get to the next hop, and that's it. And hopefully the next hop knows how to get to the next place. Okay, so there's a figure here that shows how this works. Here's a comparison. So the interior guys, how fast does it take to update the routing table? Well, it's tiny, right? I only got like 400 machines. Jeez. How much processing does it take? Well, okay, it does take a little bit. All routers in the network, everything's connected, no big deal. The exterior guys, this is the big guys, right? How long does it take to update them? Ooh, ouch. Those routing tables are huge. So that I could, for example, I could do routing updates every 5 minutes over here if I wanted. That'd be kind of excessive, but I could, right? Over here, you couldn't even get one done in 5 minutes before you set the second one. These suckers are too big, so this takes a lot longer. Hours for the update, not minutes. Okay. Processing needs, well, no, they don't quite need so much processing for the updates. They need the same kind of processing for passing packets before there's not really issues. Who do I talk to? I talk to only my neighbors. That's it. I do not know how to get to Lampasas. I do know how to go to Copper's Cove. That's the only thing I know. I do not know anything other than the people immediately touching my edges. And then, how's the information changed? Well, I send it to everybody. Now, thank God there's not first of all, here's a good question. How many autonomous systems are there? Well, there's a couple 100,000. How many in the U.S.? About 200 maybe. Somewhere in that range. 200 to 400 autonomous systems in the U.S. So, yeah, if I wanted to send updates to everybody, I would have to send it to all my neighbors. And then those neighbors would have to send it to all their neighbors. And their neighbors have to send it to all their neighbors. And you can see how I imagine this could take an awful lot of time. There was one particular protocol that was kind of not in use now. And somebody actually calculated that, whatever, I'm making this up, because I can't remember the number, but it was like 10% of all traffic on the internet was updating these dang tables. We need something better. So that prompted him to come up with a slightly better routing protocol. Okay. In the book, on page 280, they talk about a story where there was a mistake. So they talk about in China, China could be like, the entire nation could have a single autonomous system. I don't know if that's how that works, but they could. It could be state-run. And so there's no commercial versions. So that's all there is. And so they updated. Somebody sat their machine and typed in some stuff and accidentally hit the wrong button and sent out a routing update to all the rest of the neighbors that accidentally started routing traffic that was like, in Europe, going from Spain to France, which normally would be a shortcut, went from Spain to China to France. And so, performance dropped like a stone and latency rose like a hawk. And everybody went, what's going on? Well, this shows you the nature of how these autonomous systems work. Autonomous systems basically are very trusting, and they kind of sort of say, well, I got an update from my partner, and, I trust my partner, so I guess this is legit. I mean, there's no vetting process. There's no review. Oh, let me check, see if this is right. So if you accidentally put the wrong number in an autonomous system, anybody can screw up the internet. Okay, it's kind of weird. Now, let's take that one step further. Let's talk about deliberate modification. Okay, so let's say you're in a repressive, I can't say that word. Anyway, a bad place, some sort of regime that's trying to do censorship. You could alter the autonomous system in your country and perhaps even mess with the DNS servers from last chapter, so that when people trying to get to Google searches that that are bad for your nation, it redirects them someplace else. So yes, you can use autonomous systems to do bad things. Is there some sort of governing body that makes sure that doesn't happen? No. Is there any way we could combat that? No. So if somebody wants to do something bad inside their autonomous system, they quite literally are autonomous systems. Yes, you can do bad things, and there's not much we can do about it. Okay. On page 282, they talk about router aggregation. So essentially what they're trying to do, in the simplest terms, is I want to shrink the amount of information in the routing table. So I might want to just pick, if you go back to this guy, whoops, not this guy, I meant to hit that. There's an awful lot of duplications in here. I mean, for example, look how many 174.556s there are. So you could kind of scrunch this down and say, like, this is a known path, okay? And you could, most of the time you call this like a backbone link. So instead of having all these options out there, I could just have a thing that's called the 174.561 backbone. And that way I can scrunch the size of the table up. So instead of being 900 megabytes, maybe it'll be 400 megabytes. It's just scrunching it up. So router aggregation is all about, I've got 5 networks on this side and 5 networks on this side, and they all use the exact same autonomous system path to get to each other. Why don't we just scrunch them together? Reduce. Now, instead of having a routing table that has 5 entries over here and 5 entries, now I only have 1 entry and 1 entry. It's just an accounting trick to squash down the number of items in a routing table. It's pretty cool. This is a good place to stop for the 15-minute mark. We'll pick this thing up again in just a few.